collision, you're always going to first work out the whole momentum, all the momentum stuff, and then you're going to work out the kinetic energy. But what you need to remember is that energy is a scalar. So that is how they catch people again, because you think that, so if you are looking, that same example that I had last time, so if you have 10 meters per second going that way, and now you've got 10 meters per second going this way. So before the collision, this is the velocity. So let's say we say towards the wall is positive and away from the wall is negative. So you know now that we can work out the change in momentum and all that stuff. But if I now say, what is the kinetic energy, the change in the kinetic energy? So if you say kinetic energy before the collision and kinetic energy after the collision, so what a lot of people do is they say, okay, this is going to be half, the difference is going to be 0. So please remember the difference is not 0, because when you do half mv squared for before the collision, if this is 1 again, then the v squared is going to be 10 squared. But for this one, it's also going to be half mv squared, and this v here is going to be 10 squared, and this v here is going to be minus 10. But that whole thing is squared. So that means this is going to give us 100, and this is going to give us 100. So just be careful that energy, and that is the big misconception that people have, is energy is a scalar. So you don't put a minus and a plus with energy, not really. You can say energy is lost or energy is gained, but we don't generally say negative energy. Okay, so just lost and gained. So be careful for the multiple choice questions where they do this. So the only place where, and a common one where, and I've seen teachers get this one wrong, is if you have those explosion type questions. Because when you have this, and you have the person moving this way, and then the ball moving this way, and they say, and you know that, so EK again, then remember EK before, nothing is moving. So initial EK, because the velocity is still half mv squared. And you need to remember that then, before the collision, the velocity is 0. So it's always going to be 0. This part is the part that people miss. But then after the collision, then EK final is going to be half mv squared for the person, plus half mv squared of the ball. And because they're both going to end up being positive answers, it's going to be a big answer. It cannot be 0 ever after the collision. So in any explosion type question, kinetic energy can never, ever, ever be conserved. So it can never be an elastic. So yeah, please remember this. Never elastic. They ask this in multiple choice questions in all kinds of shapes and forms, but it can never ever be elastic. Okay, so just one to look out for. But then when you get a question like this in the exam, the first one is done for you. So I'm just going to talk through it, but I'm not going to actually do it. But for you, what they do here is you've got the velocities and everything here. Now, when you're working out EK before, they did put a plus and a minus. So this one was 2 meters per second, and this one was minus 1,5. So they left the negative out here. You don't have to leave it out. You can put it in, because 1,5 times 1,5 is still going to give you a positive answer. So the kinetic energy before is going to be half mv squared. So this is actually negative, but a minus times a minus will give you a plus, gives you the 3,7. Now when you start the question, please remember you have to do EK before, get an answer. Then do EK after, get an answer. It has to be separate. If you start from the beginning saying that they are equal and they're not, it means you're doing bad maths and they'll take off marks for you. So please make sure that you do them separately first. First EK before, then EK after. And then you say, therefore, elastic collision because EK initial is equal to EK final. So write that step in, because this is going to definitely get you that one extra mark. And don't do them in one. Don't do it in one calculation ever. I've seen too many people lose marks for that. So don't do that. Okay, so let's do an example and then we can look at the test. All right, so a boy of 50 kilograms runs at 3 meters behind a cart. So this time the boy is moving. Okay, I'm just going to assume that the boy is moving to the right. So let's say that's our boy. And then the cart is also moving to the right. I just like doing diagrams because then you can put your information in here and it makes, so your boy is 50 kilograms. Normally they give you a diagram, but if they don't, just do it. 200 kilograms, quite a heavy cart. This is 3 meters per second, and this is 2 meters per second. And then they say calculate the velocity of the boy and the cart after he jumps onto it. Okay, so this is not elastic. Oh, it's not an elasticity question. It's a conservation of momentum question. But I want us to then say, okay, was this collision elastic or not? So we're going to add that question at the end and say, is this an elastic collision? But how first will we get the velocity of the boy and the cart? What are we going to use? Are you going to use change in momentum or conservation of momentum? So remember, change in momentum is delta P, and this is normally for one object. Now there's two objects. So if there's two objects and there's something that happens to them that their velocities are changing, that's normally a sign that you are going to use the sum of the momentum's initial is equal to the sum of the momentum's final. So now because they are moving separately before, we're going to say M boy V U boy plus M cart U cart is equal to, and then they are moving together. So remember, if they are moving together, you can add their masses together. So you can say M boy plus cart, and then they're moving at together with one final velocity. It's always when they join, it's like one of those where they hit each other and join up. Now we can put our values in. So we know the boy is 50, moving at 3 plus 200, moving at 2. And then this one we're going to just add the masses. So that's going to be 250, and we can work out V. I actually do have a calculator today. You can work it out, and then you can just check if we get the same answer. I've calculated with no glasses, but I can kind of see. I get 2,2. Did you get that? Okay, so 2,2 meters per second. And our answer is positive. So can I just leave it like this? No. So if there was a diagram, you would use the diagram. But because we did this, we can say, so we decided that to the right was positive, and therefore we can just say to the right. Remember, as long as you've put it anywhere in a diagram or any indication that you've decided that to the right is positive, then you can use left and right. Keep it simple like that. But now, for the next part, we need to decide about, is it elastic or not. Now, if we want to know whether it's elastic or not, what are we going to do? Okay, so please remember, like we said earlier, do them separately. So you're going to really just say EK initial, and you're going to split your page. Then do EK after. EK final. Okay, don't be tempted to do them together. So, but now you must you must think about everything that's moving before the collision. So we've got the boy moving, so that's half M boy v boys. That's half M cart v cart squared. And then this one here is going to be a half, and again they're moving together. So the mass is again, you can say boy plus cart v squared. Okay, so this should actually be used because it's in it. Doesn't really matter, they won't mark that wrong. So now that we have this, we can just fill in our values here. So the boy is 50. I'm going a little bit fast, but so just stop me, but I'm assuming these ones are, it's plug and play. Once you have the equation, you just put your values in here again. Just remember this is not momentum. So you have to put the half and you have to square the velocity plus half. The mass of the cart is our 200, and this is going to be 2 squared. And then you get an answer and you actually write down that answer. Okay, I'm just getting it for us again. You can also do it and just tell me wrong. What did you get? 625. Yeah. And remember it's energy, so it's in joules. And energy can't have a direction, it's a scalar, it cannot be negative, so just 625. And then we're going to do the same here. So we're going to say half, and now we add their masses together. So we can say that this is 250 again. And we've calculated the V, so we know that the V is then going to be 2.2 to the right, so it's positive, but it doesn't matter because we're going to square it and it's going to end up being positive anyway. So we can 0.5 times 250, 2.2 squared, I get no, I definitely made a mistake. I said 202 squared. 2. 2. We did 605. 605 joules. So it's not far off, but it's still not the same. So now we can answer the question. Only once you have the answers, you answer the question. So what do I need to say? Okay, so you're going to say, therefore, it's an inelastic collision. And say why you're saying this, because EK initial is not equal to EK final. Because this last conclusion part, a lot of people leave this out. And that's actually what the question asked for. So make sure that you write that. The EK initial is not equal to EK final, and therefore it is not an elastic collision. Okay, anything here that bugs you, is this fine? Okay, great. I want to do actual, so there's a few examples at the end. I must remember to send you the answers for these before you write your test. I just want to do an elastic collision one. Yes, number 4. Let's do an elastic collision one before we go to the test. Before number 4 does ask for elastic collision. All right. Oh, so it's just one object. I'm actually glad they're doing this because that's still an elastic collision. So, well, I mean, it can still be an elastic collision. So they can still ask you these questions. The only thing that is difficult is sometimes it works out that momentum is actually not conserved. And that is a problem because now you can't say that it's elastic collision because momentum is not as it was before. So yeah, let's just be careful with these ones. But let's say the squash ball is coming this way, 30 grams. So immediately we're going to say it's 0.03 grams. And it's striking the wall at 40 meters per second. And then it bounces back. And they don't tell us what the velocity is. We don't know what it is. But they do tell you that the magnitude of its momentum change is 2,1. So what's the symbol for momentum change? Perfect. So they're giving us that delta P is equal to 2,1. So as soon as you get that, you know that you're gonna write down the whole impulse, jab, fat, math thing, and you're gonna just, oh, now I'm writing an A, that is ridiculous. Sorry, M delta V. And then you're going to think which part of this equation are you going to use? Let's see what they give us. So in the question, they say the ball is in contact with the ball for approximately 0.02 seconds. So they're giving us that. We have this. They've given us that, and they calculate the force. So now you can see how easy it becomes. Once you have it like that, you know that you're going to use the equation that says delta P is equal to F delta T. The delta P is given to us, but now you need to think about signs. Remember, here signs are super important. So if you decide that this 40 is positive, now that's towards the wall, what is the 2,1 going to be? This is the tricky part. You need to think what is causing the change in the momentum. So it was heading towards the wall, now it's heading away from the wall. What is causing that change in momentum? The wall. So remember the definition for impulse is that first equation, not the second one. So here, this is the definition of impulse. And that is the force, or the change in momentum is directly proportional to the force and the contact time. And it's the force that is causing the change in momentum, which is the wall in this case. So they're asking us calculate the force exerted on the ball. So that means we need to, the force is then from the wall on the ball, which means it's to the left. And that means this, if to the right was positive, then this answer must be negative. So be careful here. Well, otherwise, if you don't get if you don't have the it wouldn't. If it's velocities, it will be wrong if you don't put the sign in. Yeah, you'll still get the right answer, but in the end, because they say exerted on the ball, you still have to add the direction. And on the ball is ending up going to the left, so you have to add to the left to your answer if you didn't put it in your calculation. But I would say safest is to say, okay, this is minus 2,1 is equal to F times by 0,02. We really need to add the answers into this book. So you're going to do that calculation. And I get 105, I hope that's right. So I get F is equal to a minus 105 newtons. And now as soon as you see a negative, hopefully it will wake you up to the fact that you actually have to put a direction. Because they say calculate the average force and not magnitude of the average force, you have to remember to put the direction. So go back and say, therefore, what did the question on? The force of on the ball. So you're going to say, therefore, F on ball is equal to 105 newtons to the left. If there was a diagram. If there wasn't a diagram, remember you need to think of something in the question that you can use. So what could you use if there was no, if you didn't draw a diagram? Yeah. So please don't say against the direction of motion, or use something solid in the questions. Away from the wall would be the best one. Alrighty. Now they say, what is the velocity of the ball after bouncing off the wall? Okay. Now we can check. What are we going to do? Now, what are we going to use for that? It's still one object. So we're still going to use F delta T equals M delta V. Am I making a capital V? M delta V, and that is going to be equal to our delta P. I'll just wrote it the other way around, but it doesn't matter. So we're still going to use this. We have a lot of information now that we can use. We have this one still. We have all of this now. We've got the force and the time. We know the mass. So actually the only thing that we don't know is delta V. So that's probably what the question is asking. Let's see. They say, what is the velocity after bouncing off the wall? So if you remember that this is V minus U, then you know that's actually what they're asking us. They want to know what is after bouncing, so that's V they're asking for. And then you just decide on the part of the equation you want to use again. Now I would say use this, even though you've worked out the force, there could be a small mistake in working out the force. So go back, if you can, always use values given in the question. So I would just use that and say delta P is equal to M delta V is equal to M V minus U. Then we can put in our values. Now again, here you will not get away without having the sign right. So here you're going to have to say minus 2, 1 is equal to 0,03. Our V is what we want, and our U was 40. Because now the sign needs to tell us the direction. Although you instinctively know what this direction is going to be, make sure that the actual answer is giving that. Otherwise, there's something that you've done wrong if it doesn't make logical sense. So I would say then minus 2, 1 divided by 0,03. I always do get rid of the things outside the brackets first. And then we're going to say plus 40. Yeah. Seems wrong. Oh no, it's fine. Oh no, I didn't use a minus. Minus 2, 1 divided by 0,03. Yeah, it does work out. Plus 40. Okay, my answer was not making sense in my head. So I get an answer of minus 30. Is that what you get? Okay, and what will the unit be? Good. Meters per second. And then you need to add direction, because I didn't say magnitude. So now again, you're never ever going to leave your answer as a negative. We don't need that again later. So you're not going to leave your answer as a negative. You're always going to say therefore, and go back to the question and say, what is the velocity of the ball? So you're going to say, therefore, velocity of the ball is equal to, and give your answer as a positive 30 meters per second. So what would you like the direction to be here? Because we have a diagram, absolutely, yes. You can say left because we have the diagram, or again, you can say away from the wall. Perfect. Okay, then they say, is the collision elastic? And you need to use calculations to prove your answer. So this is the new part for tonight that we don't need anymore. So if they're asking us if it is an elastic collision, again, what are we going to do first? Right, you're going to work out the kinetic energy before and after the collision. Let's get rid of that. So we don't come up there. Oops, weird. So we're going to do it separately again. So EK initial is equal to, and it was only one ball, so it's going to be a half. So you can actually, it says use calculations, but this is actually silly because you're going to have 1 mv squared on that side, and you're going to have half mv squared on this side. And you can see clearly because the mass is the same. So here we've got the 0,03. This is going to be 40 squared, gives you an answer. And because the mass is constant, there's only one object involved. If the speed changes, it means it cannot ever be elastic. Yeah, that was 40, and then this ends up being 30 squared. So it can never be elastic because the answer will, as soon as the velocities are not the same, but be careful. If there are two objects involved, then you can't do that. So once you get the answers, you're just going to say EK, that's EK in final. So EK initial in this case is definitely not going to be equal to EK final. You can even leave the calculation there because they didn't ask you for the kinetic energies. From there, you can already see, remember you do want to save time in a physics exam. So you could leave it there and just say EK initial. If the masses are the same, you can say therefore initial is not equal to EK final, and therefore it is an inelastic collision. But now this is the one I want to show you, so you can ask your teacher and see what they come up with. Because now if you look at this one, and we look at the momentum before, so we look at the momentum and we say the momentum initial, let's make it U, mu, is equal to 0,03 times by 40. So that gives you an answer. So this is initial, so momentum initial. Then we're going, and it's to the right. So now we're going to say momentum final is equal to mv, which is 0,03 times by minus 30, which is equal to whatever the answer is. But you can clearly see that momentum initial and momentum final is not equal. So momentum initial is not equal to momentum final. And now you must be careful. So even if this was 30 and 30, no, then it would be elastic. So now in this question, they say in an inelastic collision, momentum and kinetic energy is conserved. And in an elastic one. And in an inelastic one, only momentum is conserved. But if you look at these examples, and there are plenty of them in the matric final papers, in the past papers, if you go and look at these examples, then you're going to see, okay, oops, what now? Momentum is actually not conserved. So can you call it an inelastic collision? Because our definition of an inelastic collision says that only momentum is conserved. And actually momentum is not conserved. So it's a nice trick question that you can ask your teacher. Because actually now, so they don't often ask this anymore, because this is what I'm saying it's quite a big misconception, because now you can't say this because there is actually some part of the wall that is moving. So even if it's ever so slightly, as the ball hits, it actually interacts with some particles here on the wall, and it does make them move, even if it's just vibrating in one position. It does make those particles move. So they actually do have some kinetic energy, and therefore they do have some momentum. But if you want to work with their momentum, then you must also work with their kinetic energy, and then maybe it's not an elastic collision. So they can't include the wall in these questions, because for macroscopic, on a big scale, there's never going to be a movement of the wall. The wall is remaining still. So that's the part that people miss, that there's actually, on a microscopic level, there is some movement. So you can ask, do you ask a lot of questions in class? So that's a nice question you can ask. Challenge them a bit and see what they say. Okay, so this is not really elastic and inelastic, but it isn't a bad question because they're saying calculate the amount of energy lost. So as soon as they say that there is energy lost, then you know it's an inelastic collision. And then what happens to this energy is that it's converted into sound or light or heat energy. Anything that goes with friction. And then this is the question where it says, if the time of the collision is increased, how does this affect the driver? So remember, that's the less hurt. So you're going to use the equation that says F delta T equals M delta V. You can just expect this question in your test. It's always there. Either less hurt or the follow-through question that we did last time. So the less hurt is always going to be F. You write it in terms of F because it says the safety. Safety is always we want to hurt less. So you're going to write it as M delta V is equal to, over delta T is equal to F. This is F net. Then you know that the mass remains constant. The velocities actually remain constant because it's going to hit at a certain speed and it's always going to go to 0. So this is going to be its U and its V is always going to be 0. So this doesn't change. So delta V is constant, and only if those are constant, remember, then you can say that F is directly proportional to 1 over delta T, and therefore as the time increases, the force decreases, which means less hurt. And so this type of question, like I say, it's either this one or the follow-through question, but for the follow-through question, they will always ask about the speed. Always. Okay. Let's see if there's anything else. There's a graph. Let's look at the graph. Okay, so they say a stone is thrown vertically upwards and allowed to fall freely. So the stone is doing this. Which one of the graphs represent the momentum as a function of the time? Now remember what the momentum is. The momentum, it's not change in momentum. Be very careful. The momentum is just m times v. So if you're looking at momentum, mass is constant. So that means the momentum is going to look like the velocity. And if you learn your definition, so this is actually kind of testing your definitions as well, because your definition for momentum says that it's the product of the mass and the velocity, but it also, just below that in the SAG, says that the momentum is in the direction of the velocity. So that if this is left, this is going to be, if the velocity is left, the momentum is going to be left. Makes sense because it's moving in that direction. So now, if you think back to your velocity time graphs, they looked like this. Okay, remember this is going to be, so this graph took up as positive. So it's going, this is while it's moving up, it's that part there, it's slowing down, slowing down, slowing down. And as it gets, remember V at the top is always 0, so that is going to be the top. And then it's going to be speeding up, speeding up, speeding up until it hits the ground. But now it's going negative, and momentum does have a direction because it's in the same direction as the velocity. So it's going to look exactly like a VT graph for a vertical motion object that we did in the previous section. So don't think it's this. This would be for kinetic energy, could be like this. Because, so EK graph would be like this. Because the kinetic energy is getting less. As it stops here, again, is on the ground. Sorry, this is max height. Again, top. And then faster until here it reaches the ground. This one is just very wrong because they said it's thrown upwards, so it cannot start with a zero velocity because it's thrown upwards. This one is also very wrong because it says that our momentum is just constant. There's no direction change, and you need to remember that momentum is a vector. So as soon as this goes from positive to negative, your momentum graph must also go from positive to negative. So that could be a little graph question that they could ask you in a multiple choice. Has your teacher said anything about the graphs that you are needing to do? Not yet. Okay. There are in these are the questions from the yellow book that we did with our boys. So you can have a look at these because I put them in the notes because they kind of mixing things. They're mixing momentum, impulse, kinetic energy, but then there's also some other conservation of energy questions, which is not in this topic. So that's why I just picked these out. So these questions, if you look at your yellow book, are all on impulse, momentum, and elastic collisions. So you can, before the test, if you can do all of them, that'd be amazing, but it's quite a lot. Okay, so those are the notes. Anything in this chapter for impulse, momentum, collisions, anything that that we did not do or that you're still confused with? Okay. So let's look at this test we gave our boys. There was it was not just on momentum, it was on fields as well. I couldn't find one that was just on momentum. I try not to do this. I try not to mix. Oh, this was actually from a past paper question. So it's and this is in the yellow book as well. I think it's just not a gun in the yellow book. Can't remember. So it says a stationary gun fires a bullet of m. The bullet leaves the gun with a momentum of that and a kinetic energy of that. The mass of the recoiling gun is 50 times greater than the mass of the bullet. So mass gun is equal to 50 times mass bullet. And also, please remember that if it's a multiple choice question, the chances are that they don't want you to do a hectic calculation. You must be able to almost logic it out because otherwise you're on the wrong track. They're testing concepts in the multiple choice, not detailed plug and play calculations. So it says, it leaves the gun with a momentum P and a kinetic energy G. Okay, so then what are the magnitudes of the momentum and kinetic energy of the recoiling gun? So they're giving you the information about the bullet. So the bullet is leaving with a momentum P and a kinetic energy E. They want to know what is the momentum of the gun and what is the kinetic energy of the gun. So you need to think now, what is the initial momentum here? 0. So, and this question did say magnitude. So you didn't have to worry about that the answers don't have negatives. Now, so if this momentum is P, then what would this momentum have to be to give us a 0? Negative P. And because the question is only asking for magnitude, we know that it's going to be either this one or this one. So those two we've already eliminated. And now for the next one, you just needed to think, okay, now what is it going to be? the kinetic energy before was zero. Can this ever be an elastic collision? No. So please be careful. This is actually the exact question where a lot of people told the examiner that why did you not put in whether it's an elastic collision or not? An explosion, like I said, could never, ever, ever be elastic because we know that EK initial is equal to zero. So that's not going to help us. We need to work with the velocity. So now if you're thinking about it, the momentums are the same. So if so this is P and this is P, but the mass is 50 times greater than the mass of P. So we know the kinetic energy cannot be the same. Now, I've been saying to people, if you see two of the same answer, it's kind of a hint that it's going to be one of them. So we already know that this is P, and now there's two of the same answer, so it's probably going to be the right answer. They're just checking if you can put the right answer here with the right answer there. So the answer is definitely B, even though we didn't work it out. But now, if you think about it, if you're thinking about momentum is going to be the mass times by the velocity, and they tell you that the the gun is 50 times heavier. So if we say that the mass of the bullet is equal to m, then the mass of the gun is going to be 50 m. So if this answer is still going to be P, if this is 50 m and I need to cancel it out, then this needs to be 1 over 50 v, so that they can cancel out and still give us the same momentum. So you can work it out mathematically, just like this, to say, okay, yeah, it's E over 40, because it only depends on the velocity. So it's E over 40, but it could also be the, or you can just logic it out with these two of the same answer, therefore it is that one. It's kind of a cheat way, but it works every time. Yeah. Move on to this one. Okay, so they've got the masses, and so they've got the scenario. He's standing still, I think. No. When Heinrich, okay, so this is Heinrich is moving east, combined mass, okay. Josie throws a basketball. Oh, the basketball has the mass. So immediately you're going to write 0.650 kilograms. That is in kilograms. So the law of conservation of momentum is easy. You can just learn that. So that is the total momentum in an isolated system remains constant. Please remember to add that whole bit about the system being isolated. Space here. Oops. Bit too much. And then they want to know, calculate the velocity at which Heinrich, at the ball reached Heinrich. So what equation am I going to use? You'll see after all the mechanics is done, that becomes your biggest question. What equation must I use? So for this one, what are we going to use? Okay, let me just write it down. Is there one object or two objects? Okay. Also, the question just asked you for the conservation of momentum. And normally, 99% of the time, if there's a law, you're going to use that law in the next question. Please start getting used to that because they do it in tests as well. So they've just asked you for the conservation of momentum. Is this conservation of momentum or is this impulse? It's impulse. So we can do this, but let's see, because you could use it, but you need a lot of information. So let's start and see. So don't get discouraged by if you use the wrong equation. Just go and see is there something else, because delta P would be the change in momentum. They did not give us that. The mass of the ball, yes, we have, but now we need to decide. Are we going to use the ball? They want the ball, yes, they want the ball. So we do have the mass of the ball. But do we have the change in momentum of the ball? They want the velocity, this is what they're asking us for. So they want the change in velocity. We have the mass, but we do not have that. And we can also not using F delta T because we don't have the time and we don't have the force. So you're going to get stuck using that equation. And also because they just asked you for the conservation of momentum, as soon as you see conservation of momentum law, the very next question, you can almost, like I say, 99% of the time, you can write down this equation after that. Because they're asking for conservation, now you're going to use it. You're going to say the sum of the initial momentums equal the sum of the final momentums. So look out for laws, they help you. Now we've got two things moving before the collision. So we've got M Heinrich, U Heinrich, plus M ball U ball is equal to, now this time Heinrich is catching the ball. So what does that, how does that help us in this equation? So you can add the masses and you can say that it is, how much is this child weigh? 66. So 66 plus 0.65, and the velocity again is, I should have written the equation first and say M Heinrich plus ball times by V, and then you can fill it in. This one I haven't filled in now. So Heinrich is 66. Oh, we haven't decided. So I'm just assuming that to the right is positive. So we're going to make that the 0.7 plus, we do know what the mass of the ball is. It's the 0.65. But this initial velocity of the ball is what they're asking us for. Calculate the velocity at which the ball reached Heinrich. So this is U of the ball before the collision that they're asking us for. So this is going to be 66.65 V. We have V. Because they say that when Heinrich catches the ball, he slows down to a velocity of 0.58 east. Oh, they gave us east. So this is east, and this, we decided that that is positive. So anything that ends up with a negative answer then would be west, if we could get a negative answer. So now we can work out so don't put a sign, don't assume a direction, just, so don't put a direction in. So this is positive, this here, this is east. So east is still positive. So the 0.58 is still going to be positive. Now we can put that in our calculators and see, and you should, without giving it a sign, you should end up with a negative sign. So let's see what you get. No, I did not. I'm typing the wrong thing all the time. I always start on the other side of the equation. What did you get? Are you there already? As if I'm very slow. What do you get? Good. Meters per second. So are you going to leave your answer like that? What are you going to say? Okay, but you can't just write where's there. That will be wrong. So you need to go and say UB, or the initial velocity of the ball, is equal to, give it as a positive answer, meters per second, and then say west. And that makes sense because the ball had to come this way to make him slow down. If the ball came in the same direction, then he would be speeding up. Then the answer would be negative, but positive. But don't ever put a negative or a positive with the answer. You can see the calculation will always help us with our direction. What am I doing? Then I think, let me just see what they ask. Yeah, normally they say prove by calculation whether this is an elastic or inelastic collision. So tell me what to do. Okay, exactly. So what am I going to write? Do they want you to write the whole thing? Are you not allowed to say initial? Yeah. No, some teachers get fussy. They don't like initial. So yeah, EK before initially. And then please, yes, separate. Don't say equal. EK after collision. Because you do not know that they are equal or not. And then you work them out. So here, what do we have moving? So it's half mv squared. What do we have moving before the collision? And what about Heinrich? Is he not moving? Let's just go back there. So it says Heinrich is moving at 0.7 meters per second east. So he is moving. And the ball is moving towards him as well. So can I just do it for the ball? No. I have to add half mv squared for Heinrich. So that's going to give us the half 0.65 for the ball. And we've just worked out the speed of the ball is 11.60. And this is the only place where the sign doesn't matter, but you can put it in as 11.60. Because you're squaring it, it actually doesn't matter. Plus half the mass of Heinrich was 66, I think. And then he's moving, let me just check. He's 66 kilograms, and he's moving at 0.7 meters per second. So 0.7 squared. And that gives you your answer for your collision before. Let's just work it out. Looks pretty small, but I get 59,902 joules. So what you get? Okay. So it's not a big answer, it doesn't matter, it's still kinetic energy. And then we're going to work out the kinetic energy after. So what is moving? Always ask yourself that question. What is moving after the collision? They are. So we're still going to say half mv squared, but we can do the same as what we do with the momentum part. So we can say half m of Heinrich plus the ball times by v squared. So that's going to be half 66,65 and our velocity after the collision, the question told us that is slowing down to 0.58. So that's just going to be 0.58 squared. And we calculate that part. Yours quite close. I get, no. You get 11.21. Definitely not close. Okay. So now, have I answered the question yet? What was that right? Okay, therefore, inelastic collision because we know that EK initial is not equal to EK final. And that gives you, can you see how many marks it is? But if you did them in